Okay, in the last lesson we discussed stress and how to take a particular stress state and transform it into principal normal and shear stresses. In this lesson we're going to take a look at the relationship between stress and strain and how to convert a stress state into the strain that is experienced at that element. So let's take a look at a review of that. The first thing I realize is there's a relationship between stress and the amount of force that's put on a part. So in a very basic tensile test specimen, you take a part that has some sort of diameter here, you screw it into your testing machine, you begin to apply a force to pull this part apart. And as we do that, we calculate that the cross-sectional area of this part greatly influences the amount of stress that the part sees. In other words, if this is a part with a very large area, the stress will not be too great, but if it's a very small area with the same force, you'll have a lot more stress induced within the part. And so a very basic understanding, and this is almost just a unit balance, is to recognize that force divided by area is equal to stress. We define strain as the change in length. So imagine at the beginning there's no force on the part and I measure some distance and call it L0. Then we put some sort of force on the part. We apply stress, and when we do that we find out that the material has some give to it. And this is the amount of give, the current length minus the original length divided by the original length. And that's what we define as strain. Now obviously this would be different if I have the same amount of force, let's say 5 pounds, that I'm applying to pull it apart. If this is made out of cheese, it's going to stretch a lot further than if it's made out of titanium. So there's a great deal of influence in the type of material it is. That relationship we often call the modulus of elasticity, or the Young's modulus, and it's basically a linear relationship between stress and strain. So this allows us to recognize for a given known material where I've already calculated what E is, I already know what that relationship, that linear relationship is. If I know the stress I'm inducing within the part, I know the expected strain that that part will receive, and vice versa. Now, E is a linear relationship between stress and strain. We know that's not really quite the case always. So let's take a look at a stress-strain curve. So hopefully this is a review. This line is a review. And this shows two different types of material. On the left-hand side we see something that's a ductile material, and on the right side we see something that's less ductile, a little bit more brittle material. The important thing for the moment as we begin this discussion is this whole calculation of E is not valid for an infinite amount of force that we apply to our part. In other words, it's going to stretch linear for a while, and then it moves into another region, and this region is really defined by the fact that when we remove the force from our part, the part no longer returns to its original position. So for ductile material in the elastic range, if I apply a stress, I'll produce a strain, and then as soon as I quit applying the strain goes right back to where it was. And that happens as long as the stress doesn't get above some sort of plastic line. It's labeled PL in the graph. If I continue on, and very often the plastic line and the elastic line are at the same place, so this is kind of no man's land in between there. A lot of materials, these are exactly the same point, or so close to the same point we consider them the same point. When I get beyond into the elastic region, notice for increasing the stress, it's beginning to strain faster, all the way into the point where I hit some sort of yield strength. And this is what's really important. This is what's going to determine whether this part is going to fail. If we put so much stress on it that it begins to yield, we're in danger of it breaking. Okay? So some types of material, you can continue to strain the material all the way until it reaches some sort of ultimate, and then if you notice, for the same amount of stress, you'll now have a decrease in the amount of strain. What this means is that if I put this amount of stress on it, S ultimate, if I put this amount of stress on it, the part's going to fail, and what's going to happen is the diameter is slowly going to get smaller as it begins to stretch, and since the diameter is now smaller, it'll be able to strain even further, and so this is what we would actually exhibit in the lab. If we take account to the fact that the surface area is getting smaller as it stretches, this is what the calculation of what's happening on the molecular level. This is a better understanding of what the stress-strain relationship actually is, but it doesn't really matter because this is how it's going to behave. That's why you have engineering stress-strain curve versus the true stress-strain curve. For brittle material, it's not quite as easy. You don't get this hump where we return back down, and so you basically have to pick where you're going to call the yield strength. In other words, a ductile material gives us a warning. We pull on it, we pull on it, we pull on it, we continue to add stress, and then we notice this dip where it begins to stretch, and the strain becomes much more noticeable at this point. And that lets us have a warning. It hasn't failed yet, but it's on the road to failure. We better make some changes. For very brittle material, you never really get a warning. Yes, you do see a decrease in the amount of strain, and if you were to ever take the stress back off, you'd realize that you've now permanently deformed your part. So you've crossed into that plastic region, but the only real warning from just looking at the part happens right here when it actually fails. Now this is not a good situation. No one wants to know your part is failing when it all of a sudden snaps. You want to be able to look down there and see that it's got some wear or something like that. So we're going to consider what's typically the standard for brittle material, that when you release the stress, if you have induced a 0.2% or a 0.002 in strain, then we're going to call that the stress that caused that to be our yield stress. Going back to this very first equation with the linear understanding of E is equal to sigma over epsilon, this recognition that the modulus is stress over strain. First we talked about that's really only true for one region that's bounded by some maximum amount of stress we can induce before we cause permanent problems. And also, that entire test is only done in one direction. So that's assuming there's no other stress in any other direction. In other words, this is just along, let's say, the x-axis. Well, now we need to consider what would happen if we do things along the x and y-axis. So first, let's just consider the 2D. So let's say I'm looking at a stress cube, and for now, all I'm doing is applying a stress in the x-axis. That's going to induce a strain in the x-axis, and we're going to denote that xx. So it's the strain induced in the x-axis by stress in the x-axis. If I put tensile stress on the part as opposed to normal stress, we would expect that that our stress cube is now going to deform. And this deformation we're going to call epsilon xy. It's denoting actually a change in angle of the parallelogram. Okay, there's two different definitions. There's engineering strain, engineering shear strain, and engineering shear strain, and the shear strain we're going to use in this class is just divided by 2. So here are the two matrices with the two different notations. So we have these strains on the diagonal that have to do, they are caused by strain from normal stress, and the off-diagonal terms are caused by strain because of the shear stress. So that gives us some understanding about what's beginning to happen in our x and y and even z directions. But now we need to recognize that there's another tensor involved. We cannot just do simple matrix math. In other words, E is not a constant for every direction of the strains. Remember, these off-diagonal terms have to do with angles, and the on-diagonal terms have to do with basically percent of change of length, while this is percent of change of angle. And so all of that combined together means that there's not just this very clear relationship between a matrix of our stress state and the matrix of our strain. So let's see if we can illustrate that a little bit better. Suppose I put a stress in the x direction. I would expect that the part is going to move in that direction, but notice what happened in the y and z direction. We can't create more material, so the material has to change shape. So if it strains in the x direction positively, it's going to have to strain in the y and z direction negatively. In other words, it's longer now in the x direction, which means it has to be shorter in the y direction and the z direction. And we know from experiments, here's our linear relationship that we've already talked about, and we know from experience that there is this Poisson's ratio that defines how the strain in this y and z direction, the off directions, relates to the modulus of elasticity. So this gives us some sort of relationship of when I stretch in the x direction, how much do I stretch in the y and z direction. Okay, so I have that in the x direction. Now if I were to do the same experiment with the y direction, I would get the same thing. I would get some sort of normal strain occurring in the y direction, and then notice the negative signs as the length gets smaller in the x and z directions. And of course, if I do it in the z direction, the same thing would happen. I would get some positive strain along the axis that I'm actually pulling, and then I would get some negative strain in the other two directions. Now it turns out that since these are three orthogonal directions, they're 90 degrees from each other, they turn out to not play, they play well together. In other words, what I can do now is superimpose these three together. So let's say now that I've now applied a normal stress in the x, y, and z direction. What I can do is I can say the contribution of stress that I applied in the x causes a strain in the x. The contribution of the stress I applied in the y causes a negative strain in the y, in the x direction, but it's induced because of the stress in the y. And the same with the z. The strain is in the x direction and it's induced by the stress in the z directions. Sum these three up, and that turns out to be the total amount of strain that I'm expecting to see in the x direction. That's great. This is now getting us to the place where maybe we can simplify this with a little bit of math. So that's applying that superposition and putting them all together. And now, if I look carefully, I have three different equations and three outputs and three inputs. And so we can arrange this as a matrix. Notice this 1 over e times sigma x, that's this term. The Poisson's ratio divided by e, negative sign, times sigma y, that's this term. And then the third one is this term. So that all makes sense. This matrix right here is just a re-expression of the superposition we just talked about before. The problem with this is only a relationship between the diagonals of the stress-strain tensor. In other words, I've only considered the sigmas. I've not considered the taus of the stress state. So when is it okay that I can use this equation? The answer is I can use just this equation when I'm considering the principal normal stresses of the stress state. So let's say I have a stress state. I've got 6 inputs, sigma x, sigma y, sigma z, tau xy, tau yz, tau xz. And the first thing I do is I convert those into some sort of principal stresses, sigma 1, sigma 2, sigma 3. Then I can get the strain in those principal directions by using this equation directly. If I want to continue to understand how it's actually straining along my original coordinate system, so I don't want to do a coordinate transformation, then I need to take care of those off-diagonal elements. So I'm not going to derive the equation, I'm just going to show you the matrix that we need to do that, and we'll discuss a little bit about what this means. The first thing that we need to do is recognize the relationship of how shear stress affects a strain in that direction. And it turns out there's this new G And the G term is the relationship. Again, E and G are both found by taking a known material, putting known loads on it, watching the way it responds, and recording it over and over and over and over again until I'm guaranteed that I understand how that material behaves. So actually that's the same with the Poisson's ratio. So modulus of rigidity, modulus of elasticity, and Poisson's ratio are all found experientially by testing parts and then applying that knowledge to this particular part. What we have here is what can be called a block diagonal matrix, and what that means is here's a matrix, a 3 by 3 matrix, here's a matrix, a 3 by 3 matrix, and it's zeros on the other two matrices. So this is kind of subdivided into 4 3 by 3 matrices. There's a lot of zeros in here, but the point is that this now gives me something. If I have sigma x, sigma y, sigma z, if I have an actual stress state, this is now applied stresses and not principal stresses, I can go directly into understanding what the applied strains are. Keep in mind, these will not be the maximum strains that are caused. These will only be the strains in the direction, the original coordinate direction of the system. Okay, let's do an example, and then we'll talk more about this in class. So let's suppose I've got a really simple stress state. The only thing that's going on is there is 1,000 psi compression stress on my stress cube, and there is also a shear stress of 750 psi. So let's take a look at this matrix. What we're going to want to do is first we need to create this matrix. And then if we take 1,000, 0, 0, 750, 0, 0, actually this should be minus 1,000, 0, 0, 750, 0, 0, multiply it by the matrix that we create, and we'll get a set of strains in those directions. So let's see what that might look like with MATLAB code. This first block is showing where I'm entering in the values, and notice there's a couple things I like to do as I'm doing MATLAB code. The first one is I always comment the units as I go. This really helps clear things up, and a lot of times it's kind of tempting to go straight to megapascals because a lot of our units are in megapascals in the back of the book. I would encourage you, when possible, go ahead and leave it as the basic value. It's a lot easier to figure out what's going on if you just keep it in the pascals units as opposed to megapascals. Okay, I'm also stating if there are no units, for instance Poisson's ratio, and then there's a conversion. This is a translation from psi to pascals. So for whatever reason, when I set up this problem, I decided to stay in the Pascal regime, so I'm transferring all of this into pascals, and then we'll come back to psi at the end. Now, if I look at this matrix carefully, there are really only 3 values. There's a 1 over g value, there's a 1 over e value, and there's a minus mu over e. And so those are the 3 values that I've set up. The next set of code is really kind of a trick. I don't mind if you never learn how to do this, but I wanted to show it to you so you have an example in case you want to do it. What I'm now doing is making a block diagonal matrix. So first I'm going to do is C up. That's this little matrix right here. And it's C2 times 1's, that's a 3 by 3 matrix. I'm populating everywhere with this C2 value. And then I take a diagonal of C1, that's this value, but I also have to subtract the one that I put on there with the 1's back here. So it's C1 minus C2. And again, this is now, so this is a diagonal matrix, and then I need to multiply it by this 1's matrix to make everything work out okay. For C down, it's a lot easier. I just take C3 times the diagonal of the 1's of a 3 by 1. So there we go. There's our matrix, and combining them, this C is this entire matrix right here, this entire C. So now I just need to enter in stress is equal to, there's our minus 1,000, 0, 0, 750, 0, 0. Multiply it by stress, and I want strain to be in terms of millimeters per meter. So notice something interesting here. I'm not, at the end of this problem, going back to standard units or empirical units. And the reason I'm not doing it is because stress or strain is often expressed in terms of 1/1000ths over 1. So if you look at the units here, this is actually just milli. That's all that left. The meters cancel. And so the strain would be the same if I put it back in inches. I'd have milli-inches over inches, if you will. So the unit works out by itself. Just have to plug this into MATLAB and I get some values here. Notice the units. It is unitless except for the millimeter, but we do need to understand that there are values associated with it. The strains along the axis are in units of length, and the strains along the angles, how the stress cube rotates around, are in angular units. So we'll talk some more about this in class, and so bring your questions there.